people, the traditional owners of the Adelaide Plains, the land that we here at the University of Adelaide are on today. We acknowledge the relationship of the Kaurna people to the country, and we respect and value their past, present, and ongoing connection to the land. I would also like to acknowledge the traditional owners of the land you are on and acknowledge that Indigenous Australians have been custodians of the lands of Australia for thousands of years. I pay my respect to their elders, past, present, and emerging. So the speaker of today's MC Summer School public lecture is distinguished Professor Kerry Mengersen from Queensland University of Technology. We will hear more about Kerry in a minute, but before, let me say a few words about the context of this public lecture. So what is the summer school and what is MC? So MC is the Australian Mathematical Sciences Institute, which is a collaborative enterprise of Australian mathematics departments with a growing membership network of over 40 Australian universities, mathematics societies, and government agencies. The common goal of MC and its partners is to strengthen the mathematical disciplines, to enhance their impact and role in Australian education, research and innovation and industry, and provide infrastructure for national and international initiatives. These initiatives roughly fall into three classes. There's research and higher education, there's school education, and engagement with industry and the commercial world. So one of the major education events is this summer school. It was established in 2003, and since then is held as an annual event for over 4 weeks in summer. It is an intensive program for which postgraduate students can choose from 8 courses from all areas of mathematics and statistics, as well as some cognate areas. For example, this year we have a course in mathematical physics. Students can take one of these courses for credit towards their degrees, and this gives them a very quick start to their postgraduate studies. It also allows students to engage in the wider mathematics community and to start networking and collaborating. The program not only offers courses, but also a range of social events, a career and a diversity event, keynote speakers, and for example, this public lecture. So this year's summer school is hosted by the University of Adelaide. And for the first time, it is held as a virtual event for obvious reasons. While the classes are online using modern online teaching tools, there are also some face-to-face events in each state. For example, I'm here with about 20 students from Adelaide who are watching the lecture, and we are watching the lecture together. So this year we have record-breaking number of 191 registered students, and this breaks the past record of 171. In addition to the host university, the University of Adelaide, I would also like to acknowledge our partners, the Department of Education, Skills and Employment, the Australian Mathematical Society, Australian and New Zealand Applied and Industrial Mathematics, and the Statistical Society of Australia. So I will hand over now to Benoit Liquet-Weiland, who's also one of the lecturers at the CS Summer School, and who will give an introduction about our speaker. But before that, I would like to remind you that this lecture is recorded. So the event is recorded on Zoom, and you can ask questions after the lecture in the Q&A section at the bottom of the screen. Okay, Benoit.
Hi, everyone. Thanks a lot. I would like first to thank AMSI to give me this great opportunity to participate to this great event. And thanks to Anna and Thomas for the organization. And it's a great pleasure for me to be part of this event and to give some lecture to students. We have some great students, pretty active, so I'm very happy of this. And also I want to thank Thomas to give me the chance to present Kerry Mengersen, which Kerry, everybody knows Kerry, but I will try to summarize all his her achievement. So I'm very pleased to introduce Kerry because she's we are colleagues now for 2015. I met Kerry in 2015, and we have a close collaboration. And so So Kerry is a distinguished professor of statistics. She's a director of for QUT Center for Data Science, and she's also the deputy director of the ARC, which is a Center of Excellence in Mathematics and Statistical Frontiers. She's one of the leader, and she's an expert in Bayesian modeling, and she has a lot of many impacts in different fields. And she's currently more focused on dealing with different diverse kind of data and more in high dimensional data between the interface in the machine learning and the statistics. And she will give you some an overview today with some application in different fields in genetics and genomics, and also a lot of in environmental science. She has been the president of the Statistical Society of Australia, and also as an expert in Bayesian. She has been the president of the International Society for Bayesian Analysis. And she got a lot of awards, and one of the, I think what was the most impressive, it was she was awarded as the first woman for the Pittman medal. Sorry for this, awarded by the Statistical Society of Australia. And so this is the highest award presented by the society. And working with her, and I can see her commitment for training the next generation of researchers in statistics is impressive, with a lot of commitment of supervision of postgraduate and PhD students. And I have learned a lot to co-supervise with her some PhD students. And just to say something more personal, because maybe you can read this on many places. So what can I say? But Kerry like playing cricket on the beach, for doing a base on the beach. And also maybe my influence on Kerry. She now speaks a little bit French, and I challenge her to tell us some word in French at the beginning of lecture. It would be nice. But I'm pleased to introduce Kerry. Kerry, it's your turn.
Thank you. Merci, Benoit. Bonsoir, everybody. That's about my French. Je m'appelle Kerry. Thank you very much, Benoit, and thank you for Thomas. And it's a great honor to be giving this public lecture. I'm going to share my screen, so bear with me for a minute. Right. Can you see my screen?
Yes.
Great. Okay, so I want to talk today in this lecture about deriving insights from new data sources. So I'm a statistician, and I now work in data science, which is at the nexus of computer science, statistical science, mathematical sciences, and information sciences, brought together with e-research and domain sciences as well. And in that area of data science now, there's a lot of different new technology, virtual reality, thermal imagery, satellites, and crowdsourcing. It's a really exciting time to be a statistician, a really exciting time to be working with data, and the people in AMSI who are working on new mathematical, new statistical methods, algorithms, and the applications of those to different areas. It's a great opportunity to be working in this new world. And so this new world involves new research centres, and the two research centres that I'm involved in is ACEMS. So this is the ARC Centre of Excellence in Mathematical and Statistical Frontiers, and I acknowledge their support. And we bring together in this centre 7 universities over 7 years. We're in the last year of this, and we bring together people in maths, stats, and machine learning around the areas of healthy people, sustainable environments and prosperous societies, really working across the whole chain from the theory through the computation, through the development of the methodology, through to the application. So as well as then ASIMS, we have a new Centre for Data Science at QUT, which is bringing together from across the university now the math, stats and machine learning, but also then the computer science. So forming this kind of data science area now and looking at, again, research, training and engagement in this area. So coming to the kind of data that we use, when we talk about data science, in the old days, we used to have data science or data, collect data by interviews. We used to have medical records and surveys that would be conducted, paper-based records. Now, of course, there's a whole lot of new technology. There's wearables. We can track people. There's sensor data, any amount of sensor data in the Internet of Things. There's satellite data, and so satellites are being used by, for example, the United Nations for sustainable development goals. They're being used for water quality. They're being used for crop detection in so many different areas now that we have such great benefit from satellite data. And there's underwater photographers, and there's also virtual reality. So many different sources of new technology that we can use. So we live in this data age. We have big data, we have small data, we sometimes have no data and we need to use expert information. We have streaming data, we have data that is really messy and data that's very diverse. So we want to know about the population, we want to know about our world, but we also want to know about the individual. And so we want to be able to use these data then to break it open, to gain insights, what the data is telling us about problems that we're interested in. And so in the mathematical and statistical sciences from AMSI and the people who are working in the summer school, it's about developing the methodology that we can use then to achieve this. How do we use these data then to gain insights? How do we do analysis? How do we then use it to better our world? So we are in an industrial revolution right now. The first industrial revolution, mechanization through water and steam power, changed the world. The second industrial revolution, mass production, assembly lines using electricity, changed the world. The third industrial revolution, computers and automation, changed the world. And the fourth industrial revolution, when we enhance those computers and that automation with smart and autonomous systems fueled by data and data science, changing the world. So who uses data science and why do they use it? Here's just a small list of some of the groups that are using these kinds of data sets, what type of data they're using and why they're using it. For example, universities may use student mobile phones to improve university planning when the students are on campus. The Bureau of Statistics is interested in new forms of data, as I said, in satellite data, but also in mobile phone data and point of sale data. So to move away from the paper-based surveys and the census data to using these new technologies to be able to learn about and improve official statistics. The Australian Academy of Sport, we work with them on using wearables, analysing videos to improve winning Olympic medals, and so on. So there's many different groups that are using these kinds of data, different kinds of technology for different purposes. So I'd like to talk in this presentation about some of our experiences in using these kinds of technologies. And I'll start with this project, which we've just had approved, so it's very new. If anybody's interested in working with us, we'd love to hear from you. And this is work that's being led by Julie Versaloni, who's a researcher in our group here. And so in Moreton Bay, which is a bay just off Brisbane, it's an ecological wonderland. It has many underwater animals. It has dugongs, it has rays, it has turtles, it has whales, and so on. And what we're interested in is being able to understand these animals, where they are, and how they move through the space in Moreton Bay, and how they interact with the marine habitats, many different kinds of marine habitats in this region, and also then how you interface that with the recreational activities, with the human activity in the area. How do we live and play together in the same area? Many of us don't know what's under the water when we go out on the bay like this or in other areas. And so how do we know what impact we're having on the underwater animals and the marine habitats? So in this project then, what we want to do is bring together citizen science, the different kinds of technologies, underwater images, underwater drones, virtual reality, and so on. And we want to integrate data, and we want to be able to communicate that back to citizens to better understand our marine environments and our human impacts on that marine environment. So the kinds of technology that we're using, for example, are 360 underwater drones. So this is a, if I just go back here. So this is what an underwater drone sees under the water. And can you hear that as well? So this is an underwater drone, and it's a 360, so we can move around. We can sort of see what's in under the water here. We can also then use drones if it stops. And we can also use underwater microphones or hydrophones. So this is the sound that fish are making under the water. And so we can use this then to be able to hear different kinds of animals and to be able to then associate that with our drones and also then with our, sorry. With our satellite imagery. So we have satellite imagery of boats. So we're interested in being able to come up with new ways that we can analyze boat activity in the bay. And so these boats then we can identify in the images, and then we can use neural networks and other techniques to be able to come up with automatic classification of boats in the bay. So this is probably a better picture of the boats. You can see here at different times here where the boats are being depicted in these satellite images. So we can build machine learning algorithms to automatically detect the boat activity in the bay, which gives us a really rich picture of human activity in this area. So we're going to bring together these new technologies in this Living Together platform. Now, I can't tell you about that project because we haven't, we've only just had it approved, but I can tell you about a different project where we've been using the same kind or similar kinds of technology, different combinations of technology for koala conservation. And so in this project then, we're interested in using thermal imagery, drones, and virtual reality and observational data to be able to better detect where koalas might be in an area and to be able to predict where they might be in the future. This is really important, of course, just after our bushfires from last year. There's quite a number of groups that are working in this area now. This work is led by Kath Lee and colleagues and a group of VRES students, our vacation research students here at QUT. So we were interested here in an area in Brisbane that was surrounded by a river and then also bordered by a residential area. And we had observational data from people who walked through this area. We also had specialist data that was, or sightings from our research team. So these are some of our VRES students who are involved in this project. We also then used drones for thermal imagery. So these drones looking like this then would take images, thermal images of koalas and be able to, again, use automatic detection methods like the satellite data to be able to identify these animals in the trees. And you can see here how it's identified a koala in a tree where we may not have been able to see that animal just from observations. So if we look at where these animals are, then we have our ground surveys, that's the presences. We also have thermal surveys, which are also giving us some presences. And we have a number of what we call pseudo absences, where we didn't see these animals. So we're going to use these data then to input into our statistical models to be able to build a map of the whole area and talk about the probability of presence in that area. Now we can use one other source of data as well, which is from other citizens or from experts. And so these experts then, we don't bring them to the area, but we can take the area to the expert. And how do we do that? We can do that through the use of 360 cameras and virtual reality. So we can then immerse the expert in these virtual environments and ask them, how likely is a koala to be here? How certain are you about that? And what are the features of the landscape that lead you to make that kind of a decision? We can take that information then and we can use it as part of our statistical modeling. So we also have variables, for example, the vegetation height, vegetation density, the foliage projection cover, whether it's a regeneration area, how far away from a path it is, and how far to the water. So the kinds of modelling that we're going to do are two types. We're going to use the presence-absence data that we have from ground observations and thermal imagery, and we're going to fit a logistic regression. We can do this in R, and this is going to give us the probability of presence given the kinds of vegetation variables that we saw. We also have our virtual reality information. So we asked about the probability, how likely is a koala to be in this area and how sure are you about that? We can match those kinds of responses to then a beta distribution. Here are some examples of a beta distribution that then can represent the kind of overall probability that the expert is telling us and the uncertainty around that. And then we use that to fit a regression just the same as before, but now it's going to be a beta regression that we can use with this kind of input data. We then can combine the estimated coefficients. And so we're going to have coefficients that are going to tell us about the impact of, or the contribution of each of those vegetation variables to the probability of a koala being observed in that area. So we combine the two types of data that we have here in this way. And so from our results, we can see that here we have the bottom line is just using the ground survey. The next line is using ground and expert information. The next one is using ground surveys and thermal imagery. And the highest one there is the ground, thermal and expert information. And so you can see here the estimates that we're getting for each of those vegetation variables and the importance of those. And then we can use this information in our models. So what it's telling us is that by combining this information, the ground surveys, the thermal imagery, and the expert information, we get very good estimates and more precise estimates for each of these parameters. And so from that, then we can build predictions. We can build predictions only on the expert information. We can build predictions only on the survey information that we have, and we can combine the information. And so these are predictive maps then of where we might expect koalas to be using the combination of this new technology. So combining this information can provide improved effect estimates and predictions. We can use these approaches to better estimate and predict the presence of koalas. And of course, there's ongoing work. We need better methods to elicit and combine information from experts and locals. We need to develop methods to combine the regression estimates that we have from the different modelling approaches, and we need to improve confidence in our citizen science data. Now, citizen science data is used in so many different places. This idea of crowdsourcing in ecology, for example, it's also used in other areas like astronomy, for identification of new stars and so on. But in ecology, there's hundreds of citizen science projects. There's eBird, Zooniverse, iNaturalist. There's a whole toolkit that's been developed in the US around crowdsourcing and citizen science. And there's platforms like Mechanical Turk where people are paid to undertake crowdsourcing activities. And some people make a living by doing that. So the question in this then is, this crowdsourcing information is coming from regular people who may not be experts in the area. How reliable are the data that they are providing? How can we consider these data in our models and build then trustworthy predictions and inferences? So I can't tell you about that with respect to the Koala project, but I can tell you a little bit about that with respect to another project, and this is our Virtual Reef Diver project. So this project, you can search for Virtual Reef Diver and be delighted for you to contribute to this. The idea of this project arose because we've been working on the Great Barrier Reef, on predicting the health of the Great Barrier Reef and monitoring this. But the reef is 2,300 kilometres long. There are long-term monitoring sites at areas on the reef, but there's a lot of area that's not monitored. So how do we get information in those areas? Well, we can use new technology. So we can use underwater drones, like we saw. We can use people with underwater cameras, and we can also use satellite data. And we can use citizens then to annotate the images that we put on this virtual reef, then to give us information about whether there is coral present or not, and we can then use that information to improve our predictions across the whole of the reef. So the type of information that we're using then is images that have been donated by citizens and from underwater drones, and we geotag those to our virtual reef. And we also use then citizens to go into those images and classify them with respect to whether they see coral, sand, algae, and so on. And that's the information then that we will input into our statistical models to then predict across the whole of the reef. So the type of technology that we're using then are underwater cameras and underwater drones, and also then virtual reality and citizen science. And so there's a lot of, this is a project that was made the finals for the Eureka Prize 2 years ago, and there's a lot of activity on our site. But we would love extra people to be involved. So please, if you feel like classifying some images, please go to the site. The question then is creating trustworthy citizen science data. How do we know that the citizens who are participating in this project in classifying the images are doing a good job? Can we just ignore the error? No. What we want to do is we want to be able to estimate the person's ability to correctly detect presence or absence of coral, and we then can do either a weighted analysis, so we can weight up the good the people with good accuracy, weight down the people with less good accuracy, and we could also just use the more accurate citizen science data. If only we had a way to be able to estimate the person's ability to correctly detect presence and absence of coral, then we could provide targeted feedback and training to different to people with different abilities. Well, this is work that's been undertaken here led by Erin Peterson and team, and Edgar Santos Fernandez and co-authors as well in our group. And one of the models that has been developed is what we're calling the 3+ model. So we use a 3-parameter model that estimates user ability, the difficulty of the tasks. So we need to take into account, are they seeing difficult images, more complex coral and so on, and also whether they're just guessing. So we consider a logistic model. So we have 2 outcomes, coral or not coral, and then we use spatial information. So images that are close together are going to have similar difficulty. So when we fit this model, we have a better model fit. We have improved correlations between the estimated and true difficulties. This is with respect to just the straight 3-parameter model without the spatial information and the additional parameters. And we also have improved prediction accuracy and better estimates. So the model looks like this. For a particular user and a particular image and a particular point on that image, we ask the user if the point contains coral or not. And then we can model that response as a Bernoulli distribution with some underlying probability, true probability, that they correctly classified coral. And then we model that true probability in terms of the latent ability of the user, the difficulty of the image, the discrimination parameter, which tells us how quickly we move from zero ability to good ability, zero probability up to probability of 1, and also then this guessing parameter. We can extend this model also to include covariates, so that are associated with ability and difficulty. And the bottom equation there is telling us about how we can have a spatial relationship between the images. So each image then is going to have a difficulty that's like its neighboring images. And so the value of the difficulty then is going to be somewhere around the average of the difficulties of the images in the neighborhood. So we'll have complex regions then, and then this will give us some sort of spatial, acknowledge the spatial relationship between the images that we have on the reef. So we can then use this information. What we're interested in is estimating then these user abilities. So in the previous model here, this is the theta I. So this is the latent ability of each user. So each user then will be tagged with this latent ability. And we can then, we have some test data in this particular study that we did. So we can look at what proportion they actually got right versus what we estimated their ability to be. And you can see that we're quite close in terms of their demonstrated ability and what we've estimated it to be. So we can be confident that we can use this model in other scenarios to be able to say, you know, which users have high ability and we could consider to be expert. So we could just use the expert or the experienced information users or classifiers, or we can, and then we can also retrain more personally the beginners. We can also use this kind of model to learn about reef health. So what are the factors that actually influence the health of the reef? So we get improved predictions of coral cover and the uncertainties, and we learn that heat waves and cyclones do have a negative effect on the proportion of hard corals on the Great Barrier Reef, and that areas that are classified as marine reserves and the middle shelf reefs, so the reefs that are not too close to the shore and not too close to the ocean, tend to have substantially higher proportions of corals. So we learn these kinds of messages from these rich models that are taking into account these different data sources from the different technologies. Now, one of the questions that we might have is, we've got lots of images now. There's a big data computation here. We have lots of images, lots of users classifying images. And so we have data sets now that are too large to be fit directly on one machine or even on a high performance computer. And so we need tricks then to be able to handle those kinds of data sets. And the kinds of tricks that we can use are really where we think about having a divide and conquer approach. So we split the data into subgroups. We fit the models to the independent subsets on independent machines, and then we combine the results into global estimates. And we do that in specific ways that mean that this combined model, the combined estimates then, are good approximations of what we would have got if we did the whole analysis. So this is also work that's really important in terms of the computation. So these new models that we have for combining and adjusting crowdsourced geospatial data outperform the current popular approaches and help us to improve the quality, the accuracy and the trust that we can have in crowdsourced data. And the methods are scalable for larger data sets. Now, there's ongoing work, of course, as with all of our research, and one of the areas is in developing better methods to analyze sensor data in general. Now, I can't talk about that with this project, but I can talk about it with another project. And this project is about being able to use water quality sensors for estimating the water quality across a network of streams. So this is an area in the USA which has a lot of waterways, and we have monitors for water quality in just a small number of areas in this region. And what we'd like to do is to be able to estimate the water quality across the whole of the region. So we use these water quality sensors that are typically, these water quality sensors are very expensive, but now they're developed cheap versions, so much cheaper, but they have anomalies. And so we can put these water quality sensors in many more places because it's cost effective, but we have to be careful because sometimes they give these technical blips in the data, and we don't know whether that's actually the reading is a technical anomaly, a technical error, or it's actually an indicator of poor water quality. So this is work that's being led by Kath Lee, also some work by Javier Perez, who is working with Benoit, and also by Puasala and by Claire, who's also working with Benoit. So Benoit is involved in this project in our ARC linkage. So the linkage partners here, we have a large number of partners who are involved, and it's a very exciting project in understanding how we can look at anomalies or errors in these kinds of data. And anomaly detection to improve the quality of sensor data is really important in many areas. We're looking at it here for water quality, but we can use it, for example, for cybersecurity. We can use this kind of information for medical diagnostics and so on. So we want to be able to understand how to identify data that are errors from miscalibration, biofouling, batteries, other technical errors, as opposed to real indicators of a system failure. So what we've done, one of the ways that we can do that is to use our experts to tell us about the types of anomalies that we might expect. So what would be a pattern in the data that we would consider to be like not standard? And then we can tag those in our data sets, in test data sets, and then develop methods to be able to identify those in other sorts of, in training data sets, we'll tag them, and then we can identify those in other data sets that we haven't seen. One of the other approaches that's being developed by, led by Puasala and by Rob Hindman is around cross-correlation. And so can the data from nearby sensors be used to help us to detect anomalies? So we can look at the cross-correlation then between up and downstream data, accounting for time lags, and then we can see if we can identify what looks anomalous, like what's a different kind of pattern between these two streams of data. We can also use then statistical methods for anomaly detection. So we have the feature detection methods that I talked about, we have the cross-correlation methods, and we can also use statistical methods, for example, rule-based, no negative values. We can have feature-based patterns in the multiple series, and we can also then have regression-based approaches, for example, ARIMA models, so time series models. So we can classify these as an anomaly if one step ahead prediction doesn't fall into what we would expect that value to be from this kind of time series model. If we do this for the statistical framework setup, then we can see that a combination of these methods, the rule-based method, the feature-based method, and the regression-based methods, can help us to classify impossible values, sudden isolated spikes, and level shifts where the sensor changes the level. We have difficulty, though, in still identifying drift and periods of high variability, and these still tend to be associated with high rates of false positives. So one of the other approaches that we've been exploring, and this was led by Benoit and Javier, was using neural networks. And so then a machine learning approach then to identifying anomalies. So these neural networks will have input data, and then they'll have certain hidden layers. So we have the computation inside the neural net giving us then the output. And so we have two approaches here, a semi-supervised approach where we train only using the non-anomalous data, and then we fit models with prediction errors, and then we predict anomalous events as those tend to fall outside the predictive interval. So we sort of say, what's the non-anomalous data look like? And then we identify anything that falls outside of that in our new data sets. We have also supervised approaches where we train using labeled non-anomalous and non-anomalous data. So then we generate probabilistic models to say, as we move through data that we haven't seen, what's the probability of it being anomalous or non-anomalous? So these semi-supervised and supervised approaches can be used with any kind of model. Here we used them with the neural network. So we looked at long short-term memory networks, and we then explored different learning methods and hyperparameter values for those models. So there's 5 steps in this neural network approach. For those that are interested, I'll just take a little bit of time to explain. So this the LSTM network is a recurrent neural network. So this is a kind of autoregressive integrated moving average approach and a nonlinear autoregressive moving average model. And it's structured in network units, so memory blocks, and they're composed of self-connected memory cells and 3 multiplicative units, input, output, and forget gates. And so this then gives us this sort of long short-term memory structure in the neural network. We then calibrate the models using a multi-objective optimization procedure. So what does that mean? The multiple objectives that we want to be able to optimize are in terms of we want our model to be accurate, sensitive, to have good sensitivity and good specificity. So that means that we'll have good probability of identifying anomalies that are really there and identifying not anomalies that when they're really not an anomaly. So we have good probability of detecting true anomalies and true not anomalies. We also want to be able to iteratively improve the distribution of the functions here. So to maximize these objective functions. So then we're going to use that approach to then select the best model for each water quality variable, environment, and anomaly type. And then we can use that approach. So what we get from that then is that our semi-supervised classification method was better able to detect our sudden spikes, sudden shifts, and small sudden spikes. And our supervised approach was better for long-term anomalies associated with drift and periods of high variability. So we can see here that these approaches were able to, within this neural network framework, we're able to identify these different kinds of anomalous behavior that we had in our data. So that's fine. We've got our anomaly detection approach, and we want to say, okay, well, what do we do with that now? Now we can identify what are the spikes in our data the different behavior that's going to be related to the technical issues with the sensors. But what are we going to use that sensor data for? Well, here's the example again. Here we have water quality data over in particular areas, and we have temperature data for the whole stream. So we have not water quality data. In this particular example, we have water temperature data, that's being taken at these points. And we also have air temperature data across the whole of the stream network. And so what we want to do is we want to be able to predict the water temperature across the whole area at every kilometre. So we've only got 42 data points, and we want to predict at 1,622 locations based on those 42 data points and on the variables that the other variables that we have. This is work that's led by Edgar Santos Fernandez with colleagues as well from the ARC linkage project. So then we have our spatiotemporal model where we're going to have our subsampled water temperature data. That's going to be our response. And we have our covariates, which are air temperature, the stream slope, elevation, and the drainage area for each of the points in the network here. So what we end up with then are spatiotemporal predictions of water temperature at the over time, of course, and over space. And we also can say, for example, what's the probability that the mean water temperature is going to be greater than something we care about? In this example, it's 13 degrees because that was the temperature for a certain type of fish that would not be able to survive if the temperature was higher than 13 degrees. This is important, for example, in climate change analysis. You can see here as time changes over the different years, what that threshold looks like. So the yellow values is high probabilities of exceeding 13 degrees. And you can see as time changes then, we're getting more yellow in the pictures there. So it's a concern about the changes in the thresholds for water temperature for this fish. So sensor data are pervasive. Low-cost sensors have great potential for ecological monitoring, but they are prone to these technical anomalies. Statistical methods for anomaly detection can help to improve the trust in the data. And these kinds of sensor data are used, as I said, not just in streams, but they're used across the reef. They're used in our buildings. They're used in our medical devices. They're used for government agencies. So it's really important that we understand how much trust we can put in these sensor technology and the data that they provide. Trustworthy data can provide really strong data-focused insights. And statisticians and mathematicians have a real role to play in being able to provide some of that trust. So ongoing work in this area is to develop other models that might be used to analyse sensor data. Now, I can't talk about those other models in this example, but I can talk about it in another example. And this example is an example of sensor data of a sort, and this is with COVID. And so I wanted to talk about how we might use COVID data in a trustworthy manner. So the COVID data then in Australia, it's of course a topic on everybody's mind at the moment across the world. So we have the current status in Australia. We have 106 active cases. We have 909 total deaths. This is as of today, and 28,786 cases. You can see there the pattern of the daily number of reported cases. So a spike early on, and then a spike around July, August last year, and then only small number of cases since then. So the question is, how do we model these kinds of data? So what we can do, what I wanted to discuss in this is that sometimes when we're looking at these more complex models, it's useful to come back to some simple models to describe some more complex processes. And one of the simple models that has been being developed by a member of our team here, Reinhard Browning and colleagues, is around using Hawkes processes. And these Hawkes processes are what we call self-exciting models. And why do we call them that? a Hawkes process or a self-exciting model says that past events influence the short-term probability of a future event occurring. So we use these kinds of models. For example, you can think of neuroscience, where we have neurons that spark and then induce sparking in other neurons. We have crime and terrorism, where a terrorist event may then induce copycat terrorist activities. So we have an event that influences future events occurring. We have seismic activity, so an earthquake that will then induce other follow-on earthquakes. We also have social media. A post will then induce other posts. And infectious diseases, where an infectious event will then have some probability of influence the probability of future events. So the image that you see here is the deaths, the daily deaths for different countries. And we wanted to see, even though there's a lot of complexity in these daily deaths, whether a simple self-exciting model or this sort of contagion model could then describe this kind of dynamic complex process. So this discrete time Hawkes process, for those of you that are interested, we have our data that are the number of events in a particular time period, and then we're going to model that as Poisson. And the intensity function of the Poisson, so how likely those events are to happen, is going to be described by this parameter lambda t. And so that's going to be the expected number of events that occur in a time interval t, conditional on the past. So then we have the number of events up to a particular time period is going to be given by n, capital NT. And the history of the events up to that time period is going to be given by capital H, t minus 1. So I'm talking about here in terms of discrete time. So we have particular time periods. The typical type of Hawkes process or self-exciting model will be in continuous time. And we talk about instantaneous probabilities. So there's a difference between thinking about discrete time processes and continuous time processes. So in a discrete time setup, then we can talk about the intensity function at time t to be the expected difference between the number of events at time t and the number of events at time t minus 1. So that's going to be how many events happened in that interval from t minus 1 to t, given the history from up to that period of time. And so, as we said, that history then will influence what happens in this particular time period. And we think about that as then being able to be modeled in terms of a base value, mu, and then also the self-exciting part here. So some self-exciting process that's going to depend on what happens in that interval. So the self-exciting part then is going to have the expected number of events in a time period, given the previous events. That's going to be modeled through that G there. And we also have the expected number of subsequent events produced by a single event. So we have a baseline event, and then we have some number of subsequent events that's going to happen by the probability or what's the expected number of events given those previous events. So when we fit this, this model, which doesn't have a lot of the, or doesn't have any of the epidemiological structure in it, it's just this self-exciting process, we actually get quite a good fit to many of the dynamics from the different countries. You can see here the observed dynamics and also then the predicted dynamics overlaid on that as well. So we get estimates then of each of the parameters, and we also get these predicted dynamics for each of the countries of interest in our analysis. The parameter values then are going to tell us, as we said, about the baseline mean of the process, the expected number of events triggered by a single event, And these kinds of parameters then we can compare between the different countries. So we have, for example, here Spain, which has a very high baseline mean, similar to the UK and China, but lower baseline values in all of the countries in the second period. So what's the second period? We have the peak wave, and then we have the downturn. So we're modeling this part as one process, and then a change point, and modeling the downturn as another Hawkes process. So then we also can look at the expected number of events triggered by a single event. You can see here the UK has a much higher expected number of events in both periods, period 1 and then also period 2. So sometimes these simple models can adequately capture the complex dynamics. The model can also quantify the dynamics of distinct phases in the pandemic and allow us to compare the country-specific dynamics. So the ongoing work here is to develop other models to analyze COVID data, and of course there's many of them. Many of the people who are listening may have been involved in this as well. And we also have some work in our group looking at different kinds of ways. But it's very interesting to see these relatively simple models, which are challenging because now we're in discrete time. They have particular challenges with the development of the model and how we can use those to describe these really important dynamics in a topical area. And we're also interested in how we might use information from other kind of technologies. Well, I can't talk about that here, but I want to finish by just one different technology that I've been interested in just recently for the last year or so. And so this is in the area of data sonification. So I want to hear the data. So what do data sound like? And can we learn something about from listening to our data rather than reading it from a graph or seeing it in an image? And so I'd like to play you then the sound of COVID in Australia. So this is the total cases in Australia. And I'm going to play at the same time, for example, the sound of the US. So the US has more cases. It starts off at a lower base. Hear the US coming up. And that's the US. So what do we make of this new technology and the data sonification? I don't know yet. It's interesting to hear it. How does it influence how we might make inferences? I don't know yet. But it is a new technology. We've seen that other new technologies are now part of our regular data toolkit. And the way that we analyze those data can really give us insights into really important problems and also the development of new mathematical and statistical theory and methodology. What this new technology through data sonification might give us, we might see, and that'll be a subject for another talk. So I'll leave it at that. I'll leave you with some references and I'll hand back to you, Benoit.
Yeah, it's okay. Thank you. So we get lots of applause here in Adelaide. Yeah, thank you, Carrie, for this interesting talk. So I open up for questions now, and I think we already have one question in the Q&A. This is from one of the students from UTS, Louise, who's together with Mari Elder in a watch party, I guess. So great talk, Carrie, and impressive French at the beginning.
Merci.
I'm curious about why you needed the absences in the koala example. Did you actually have to pre-specify locations that you would look at to assess the presence? What would happen if someone happened to see a koala that was seen at a location that had not been pre-specified for observation? Or was the process different for presence, absence, more along the lines of case control type design?
Yeah, that's a very good question. So we've looked at models which are presence only, so basically based on data that's presence only. But the logistic model, of course, requires us to have presence and absence data. And so a typical way of obtaining the absence data is thinking of pseudo-absences. So you randomly sample from places where the koalas have not been seen. Now, of course, we have an issue because there's a possibility that the koalas may be in those places as well. But we take multiple samples from pseudo-absences, and then we can develop these models. But a very good question. So, so there are still the development of presence models that only use presence data. And in fact, we have some very good people in Australia working on that. Like, for example, David Wharton's group at in Uni of New South Wales.
Thank you. So the question came from Louise Ryan from UTS. I didn't see that in the beginning. So here's a comment from Murray. The online encyclopedia of integer sequences has a listen function for integer sequences. So maybe that's interesting.
Ah, thank you. Yes, I'll look that up.
So can you say a little bit more about the sonification at the end? So what was mapped to the sound? Just the total cases?
That was just the total number of cases. So if you look at the graph, then the total number of cases in Australia goes up, and you heard it like taper off, whereas the number of cases in the US was still going up. And so that's what you could hear at the end, the series that was sort of started staggered later. So yes, it's a different way of maybe perhaps it's a way of identifying anomalies, perhaps it's a way of identifying patterns that we hear as well as we see. And also then we could overlay data. So I was also experimenting with climate data. So I actually started off by playing the temperature one day, and I play the piano about as well as I speak French, and so I had to find some other way of doing it. And but then playing the temperature and rainfall at the same time. Challenging.
So we have another question from Pat Drake. Very interesting talk, beautiful sonification. Were these continuously increasing pitch, or did you use conventional musical intervals?
This was continuously increasing pitch. So I did actually try, when I was doing it, I was trying to transcribe from base 10 to the octaves so that we would have it in the right sort of range. But this was actually, you can choose how many octaves. So it's actually quite a nice software that's online now. I used called Two Tone. So if anybody's interested, it's free on GitHub.
So here's another question from Michael Franklin. Thanks for your talk, Carrie. Many sensors require calibration, and measurements can drift away from calibration in long-term deployments. Can the methods you described used to detect anomalies and detect calibration drift?
Yes, so that was the drift that we were talking about. It's one of the features. It's a very important feature to be able to pick up when you have this drift away from the calibration. And so we were looking at the kinds of models that could identify, like obviously the spikes, so it's single spikes, differences in variance, but also then this sort of long-term drift. The neural network models were very good at this. Some of the regression models could also pick this up. Again, this is work, the sort of the feature detection in these time series is something that, the identification of these features in long-term time series is obviously an area that Rob Hindman works a lot on from Monash.
So we have another question from Sydney, from James. Great talk, Carrie. Can the Hawkes process detect the turning point, or is it fitted to explain the curve once it has been observed?
Yes, thanks for that question. In our model, we imposed a change point. So we identified where that change point could be. In our next attempt at this, we'll look to be able to estimate that. We have some work where you can estimate change points, but in the COVID analysis, we just imposed it.
So we get another question from Alex F. For scoring reliability of contributors to citizen science, did you investigate whether correlation between contributors was a useful indicator?
Good question. No, we didn't. We just took all the contributors as being independent. Obviously, their continued contributions, we modeled those, but we didn't model. In the model, we used all of the information, of course, but we didn't use any sort of association between the contributors. But good question. Perhaps that's something we could look at.
There's another question from Jinggazi Zhu. Thank you, Carrie. Great presentation. Esther here from NSW, Department of Primary Industries. Could you please talk a bit more about the Bayesian optimization procedure? What's the difference between this optimization procedure and data assimilation?
I'm guessing the person's online. Would they like to elaborate a little from DPI?
Esther, can you explain this question a little bit more?
Yes.
Oh, hi, this is Esther.
Hi, Esther. Could you please just expand a little on your question? I'm not quite sure.
Yes. So just back to that the ANN approach, you did mention we could calibrate the model, use the Bayesian optimization procedure. Because now we're interested in this like the climate change project, and we're probably gonna use the data assimilation, which gonna include this Bayesian maybe very similar method as well. So just wondering, I'm not an expert in that area, just wondering what's the difference for this Bayesian optimization procedure and the data assimilation.
Yeah, so in the optimization procedure, maybe it's a different part of the process. So the optimization procedure was really based on like the multi-objective function that we had, which was around accuracy, the specificity, the sensitivity, improving those, and also the different kinds of producers, accuracy, and so on. So we built an objective function around those, and then you can optimize on the basis of those. So that's how you can then improve the estimates at each iteration, so that you get better. You move towards an improved estimate of that objective function.
Yes, yes.
Yeah. So I know that there are others on the call too that are expert with the neural net. So anybody who would like to contribute to this, but keep going. I'm sorry, Esther.
Yeah, thank you. So just wondering, like this this Bayesian optimization procedure is probably based on the like sensor data observation. Yep. So that's what I'm curious about, because we do have like sensors installed all across the states.
Yeah. And
we probably were interested to apply this method to our further.
Okay, I see. Sure.
Yeah.
Okay, yeah, sure. So so in terms of the like for data assimilation, if you have data from the different sensors, is that what you mean? Yeah. So what we were looking at then was well, I think you would still need some sort of model. So you're going to bring these data together under a data assimilation approach, but then you're going to need some sort of model that's going to then use that assimilated data. So basically, whatever that model is, so it could be a regression model, or it could be a neural network or something that's going to bring those data together, and that's really where the data assimilation comes in.
Okay, thank you so much.
But I'm very happy to talk about it if that's if I'm on the wrong track there.
Thank you so much. I think you did answer my question very well. Thank you.
Okay, thanks, Esther.
So we have another question here in the chat from Nishant Kumar from La Trobe University. Thank you, Carrie, for this informative session. What were the major considerations in the transformation of image and thermal sensing data that you briefly touched upon?
So when we had the thermal imagery data, we used that to have an estimate or an assertion of presence of a koala, and in fact absence of koalas in other areas, and that's what we could to help us to identify the pseudo absences as well. So we had that information, which was a presence based on the thermal imagery. We also had then presences based on the records from walkers in the area who had kept records. So there'd been sort of records of observations that we could bring in. And so we had the ground surveys, and then we also had surveys from our team who went looking for koalas in a sort of designed manner. And so at particular points in the park, so they in the area, so they the area was assessed, and then a design was put in place for points to go to observe whether there were koalas present. So we had the ground survey data, we had the observed data, we had the records, we had the thermal imagery, and then we also had the virtual reality data. So in terms of the thermal imagery, or in terms of all of those data sources, they were telling us something about the asserted presence, or in some cases absence of koalas at particular sites. Now, each of those different data sources had some measure of confidence associated with them. So we actually weighted them. Now, in that particular case, we gave just a weight based on how confident we were about the accuracy of those reports. And so that weight then was used in a weighted regression analysis. So either the logistic regression for the observed data or the beta regression then for the virtual reality data. And then later on in the virtual reef diver project was when we started to estimate the ability of crowdsourced data of users and citizens, and then those estimated abilities can be used more effectively than our self-imposed weights that we put in the Koala project.
Thank you, Carrie. So it seems as if we have no more open questions, and I think we're also running out of time. So I would like to thank you again, Carrie, for this exciting lectures. It was interesting to see so many sort of different areas of applications of what you're doing. So very interesting. Thank you very much.
Okay, thank you, Thomas.
And I think with this we conclude the public lecture. Thank you again, and thank you to the audience, and goodbye, everyone.
Bye.